All right, in this worked example, we'll be looking at the question 2. State what is meant by kinetic energy. Kinetic energy is energy due to an object's motion. Energy of motion. So keywords like due to an object's velocity. We know how to calculate kinetic energy, hopefully. 1/2 mv squared. But make sure you give a statement like this. Don't just write an equation down. A cannon fires a shell vertically upwards. The shell leaves the cannon with a speed of 80 meters per second and a kinetic energy of 480 joules. The shell then rises to a maximum height of 210 meters. The effect of air resistance is significant. Show that the mass of the shell is 0.15 kilograms. So kinetic energy, right? There's the equation. They tell us the kinetic energy. They tell us the speed, right? They give us the kinetic energy. They give us the speed. They want us to solve for the mass. And so, or show that the mass is this. So we should be able to just sort of rely on that equation for kinetic energy. If we plug in 480 joules and set it equal to 1/2 the thing we want to solve for times the velocity of 80 meters per second squared, and then solve this for m, we should get 0.15. So let's take 80 squared, 6,400, times it by 1/2. And so 480 equals 3,200 m. Divide each side by 3,200. We get m equals 0.15 kilograms. Check. For the movement of the shell from the cannon to its maximum height, calculate the gain in gravitational potential energy. So this is just, it's giving you the height. And the gravitational potential energy equation is mgh. We just showed that the mass is 0.15 kilograms. We can assume this is happening here on Earth with a gravity field strength of 9.81 newtons per kilogram and the height 210 meters. So 0.15 times 9.81 times 210 equals 309. So it's a 309. The work done against air resistance. Work done against air. So if we had 480 joules of kinetic energy upon launch, but we only gained 309 joules of gravitational potential energy, we're missing some energy. So you should always be sort of thinking about the energy budget should balance. When it doesn't, there's some energy losses due to wind resistance usually, and that's exactly what they ask us to calculate. See how everything is in joules, so it's just really the difference between those that explains the 1 mark. So it's like all the work that didn't, all the energy of motion that didn't show up as potential energy must have been lost along the way as sort of work done against air resistance. So we'll take our 480 minus 309. Get 171 or just 170 we'll round it to. And then it says, determine the average force due to the air resistance acting on the shell as it moves from the cannon to its maximum height. And so it's really about relating, you know, sort of the specific quantities to what we've already kind of worked through here. So if we've just solved that the work done is 170 or 171, work equals force times displacement. 171 joules of work done against air resistance means what was the average force due to air resistance if it traveled a displacement of 210 meters up, right? So that was the height that was given. So 171 divided by 210 gives us an average force of 0.81 newtons. it says the shell leaves the cannon at a time of t equals 0 and reaches maximum height at t equals t. On figure 2.1, sketch the variation with time t of the velocity of the shell from time t equals 0 to time t equals t. Numerical values are not required. So we have to kind of think about how is the velocity going to go as it reaches maximum height. So we know at time t, it reaches a velocity of 0, right? Because that's at maximum height. That's when gravity has slowed it down to a speed of 0. Vertically, right? And so it's not moving sideways. So all of its velocity is in that direction. Its initial velocity is non-zero, is 80. And then the simplest thing would be, oh, it just goes down like this, right? It just goes sort of decreases uniformly. That would be the case if we had uniform deceleration. So in other words, if we were to take the slope of this straight line, then the slope of a velocity time graph gives acceleration, and this would be deceleration. And so if wind resistance was negligible, that would be a straight line because it would just sort of slow down uniformly under the influence of gravity's acceleration or gravity slowing it down. But there is wind resistance, right? And so there's an extra force there that's acting. And so that decelerates it more rapidly. But it's constant, right? It's an average force. And so I think it might still be a straight line. It's just going to happen more quickly because you'd have, well, hold on. Velocity is proportional, wind resistance is proportional to velocity. So we'd say the faster that it was moving, the more wind resistance there was at first. And so it would have lost more velocity quickly and then leveled out like this. And so that's the curve I think we want there. Is it shouldn't be a straight line, but it should be, it's steeper here and then it levels out. Always start with like, here's our, it says numerical values are not required, but we know this is 80, right? It was launched at 80, and we know at the top of its flight, it's going to be 0. And velocity, drag force, okay, is proportional to either velocity or velocity squared. It kind of depends on how far you're falling. So, but that's sort of the physics that we know, is that it is proportional to velocity. So you're going to get the most drag force right away. Well, we calculated a moment ago getting this tug of war with my scroll bar like I was the other day. What we calculated a moment ago was the average force due to wind resistance, right? And so we're just sort of averaging it over the entire part of the motion here. Determine the average force due to air resistance. But it's actually going to be true that there was more drag force when it was going faster. When it's going slower, it's crashing into sort of less air, right? So if you're moving very fast through air, you're crashing into a lot of air particles, and the force due to that drag is going to be more pronounced. So it's going to create more of a resistive force and sharply decrease the velocity. And then as we slow our speed, because this is true, or or this is true, right? Then the drag force won't be as pronounced, and so it'll start to level off. So that's what I feel is a pretty good answer for that one. I think that might be close to the end of this question. It just says the force due to air resistance is a vector quantity. Compare the force due to air resistance acting on the shell as it rises with the force due to air resistance as it falls. And so as it rises, so it's always a resistive force. All right, so as it's rising, the resistive force is opposing it, right, pushing down. As it falls, the shell is falling through the air, right? And so then the force sort of pushes back up on it. So it's always resisting the motion. So you kind of want to put into words, sort of that idea. On the way up, the direction of this vector is down. Compare the force as it rises and it falls. You could also say something about what I just mentioned. It's going to be the most dramatic downward force right away when it's moving the fastest, and then as it slows down, it sort of becomes weaker. That idea might be contained also. how well we did. All right, and we've got energy due to motion, speed, velocity. Got the equation, 0.15, good. Did we get 310? 480 minus 310, 170, good, good. A curved line from a positive value on the v-axis to t, so there we go. The magnitude of the gradient decreases. That means it's curved and it starts out steep, but then the magnitude of the steepness decreases, and that's what we showed. And then the last one, as the shell rises, force decreases, and as shell falls, force increases. As shell rises, force is downward, and as it falls, it's upward. So those are the two ideas, right? It's decreasing because it's proportional to the velocity. So I feel like we did a really good job on this one. I think we nailed it. Well done, everybody. Oh.